Okay, so in question 18, we have a context where we are trying to calculate the speed of a proton after it accelerates from rest through a potential difference of negative 275 volts. And we're given the mass of the proton in the question. So this is related to sort of the links between electric potential and electric potential energy. So we have this expression delta V equals delta U divided by Q. So for an isolated system, which I'm going to assume is true in this case, is that the total energy is equal to 0. There's no change in energy, so this potential difference will be set up by an electric field, and I'm going to assume that the source of the field and the proton are an isolated system. So there's an increase in kinetic energy of the proton, there's going to be a decrease in delta U, such as there's no change in the total energy of the system, that there's no external forces doing any work on the field charge system. So I can say that the delta U equals, plus the delta K is equal to 0, therefore the delta U equals negative delta K. That will allow me to solve the problem. So now I can think of that the delta V is equal to negative delta K divided by Q. And I can then state that the delta K is equal to negative delta V times Q. That's if you not to confuse those with U's. So our delta K, the proton is released from rest, so its initial kinetic energy will be 0. So this delta K will be equivalent to its final kinetic energy. So I have 1/2 mVf squared. It will be minus 1/2 mvi squared, but I'm just restating that the initial speed is 0. So this is going to be negative times negative 275 volts times the charge of a proton, which is a unit charge, 10 to the minus 19 coulombs. If you rearrange, so if I rearrange for V, so Vf would be 2 times 75 volts times the charge of a proton, all divided by the mass of the proton, which is given in the question. There's a minus 27 kgs. That should give you a speed of 2.3 by 10 to the 5 meters per second. So choice B.